Okay, we are continuing our discussions about the econometric modeling, model specification, and diagnostic testing. Okay. Applied econometrics cannot be done mechanically. It needs understanding, intuition, and skill. Okay, you have to remember this. You need understanding. Okay, for example, I explained already for you. If you have data and you have problem, don't give up. Okay, make some corrections. If also you still have the same problem, okay, you can discuss with your lecturers. Okay, don't worry. Okay, we always available to help you. Okay, intuitions. Maybe you have a wrong model or wrong estimated model, so you can change your model with another model. Or don't worry, because we have also skill to make some corrections. Okay, because for example, we have a long experience about the econometric. Of course, we have a lot of models in econometrics. Okay. Okay. I have a student, a graduate student. She has problem about the data. After having problems, I said to her that don't worry, we can run your data by a lot of model here. Okay, I want to show you, for example, here. Yeah, in the okay, we have a lot of estimation model here. Okay, we have GMM, limited information, integrated regression model, ARS, binary, order, sensor, integer font data, quantile, GMM, GLM, etc. Okay. Okay, we do not use this one. Okay, for our model. Yeah, in previous generalized linear model. Okay, for example, this one. We have almost the same also, exactly the same. We have generalized. Okay, so don't worry if you have problem about your data. It is normal in econometrics. Okay, we generally drive across bridge without worrying about the soundness of their constructions, because we are rationally sure that someone usually checks their engineering principles. Okay, so this is about the model. Okay, one of the assumptions in classical linear regression model is that our model is correctly specified. Okay, if our model is not correctly specified, so we can make some corrections. In particular, we examine the following questions. Okay, how does one go about finding the correct model? In other words, what are the criteria in choosing a model for empirical analysis? And the second one, what types of model specifications error is one likely to encounter in practice? What are the consequences if we make some misspecifications in our model? How does one detect whether there is a specifications errors or not? Having detected specification error, how to solve our problem? How does one evaluate the performance of competing models? Okay, for example, we just learn about heteroscedasticity, autocorrelation consistency. Okay, and also we have a generalized least square model. The estimated results are the same. Okay, model selection criteria. Okay, according to Henry and Richards, okay, we have following criteria. First, be data admissible. Okay, if you have article and you cannot use directly the article because maybe we have different data availability. Okay, for example, okay, if you analyze, if we are estimating about the regional, interregional trade. Okay, for example, between Aceh and Sumatra Utara, North Sumatra. Okay, I am very confident to tell you that no any data about this trade. Okay, no need to run this model. Okay, no data. Okay, even though you cry from the morning until morning, from Friday until next Saturday, no data about interregional trade in Indonesia. Okay, this one the example for the data admissible. Okay, the second one, be consistent with theory. Okay, if you use your model, first please check whether there is a more theory that construct your model. Okay, no need. Okay, don't spend your time. Okay, please don't spend your time. Don't waste your time. Okay, okay, don't waste your time to think about complicated, about sophisticated model. Okay, you need only, we only need to use the model that has the flaw. By others. Okay, you get it?
Yes, sir.
Okay, no, okay. It is better use your time to enjoy your life. No need to think how to make the sophisticated model, how to create the very high complicated model. No need. Okay, just use other people that produce this model. Okay. Okay, have weekly exogenous regressors. Okay, if you have explanatory variable that must be uncorrelated with error term, it may be added in the some situations. The exogenous regression might be strictly exogenous. Okay, sometimes we have strictly exogenous variables. Sometimes we have weekly exogenous variables. Okay, a strictly exogenous variable is independent of current, future, and past values of error term. However, some variable have correlation with residuals. Okay, exhibit parameter consistency. Okay, if the value of the parameters is not stable, okay, you can check whether the model is has parameter consistency or not. Okay, the only relevant test on the validity of the hypothesis is comparison of its predictions with the experience. In the absence of parameter consistency, the predictions will not be reliable. Okay, exhibits data coherency. Okay, residuals estimated from the model must be purely random. Okay, I explained already in the serial correlations case. Residual from this model must be white noise. White noise, that means the residual have zero mean and constant variance. If that is not the case, there is some specification error in our model. So we have to check again our model. Number 6, B encompasses. There is model should encompasses or include all the refile models in the sense that it is capable of explaining the results. Okay, for example, here I want to explain here. Okay, for example, we have here demand for certain goods is a function of its price, income, other prices, okay, and family size, expectations. Okay, okay, we have also taste, but we don't have the data of expectation and taste. So what should we do? Okay, actually for the expectation, okay, sorry, expectation can be calculated by using rational expectation model. This is an advanced model. Is we can use rational expectations model. Okay, however, if you cannot run this model, you only run, for example, here Q demand is a function of P, Y, and other prices and family size. Okay, and then for example, we get this the estimated result. For example, some of data are not statistically and theoretically. So we have to rerun our model. For example, here, maybe we have here a linear model. Okay. We can run again with non-linear one. Here, income and income square, for example, other prices and family size. So here we can check, we can test the relationship okay. How or what is the relationship? This is a normal goods. Okay, for example, it's a normal goods, or is it inferior good? Okay, or other kind of goods. Okay, and okay, by take the derivative of this coefficient to with respect to Q demand, so we can get this one whether it is positive or negative. Okay, this is another way to check our this one. Yeah, cannot be improved over the chosen model. Okay, should encompass or include all the refile models. This is the refile models. Okay. This is a refile model. This one. Okay, this one the refile models. Okay, one of the refile models. Okay. Type of specifications error. Assume that on the basis of the criteria just listed, we arrive at the model we assume as the good model. Okay. To be concrete, the model is like equation 13 to 1. This is Y is total cost of productions, X is output. Okay, we have here cube model. Okay, but suppose for some reasons, okay, we estimate this one. Okay, that means we drop one variables. Okay, since equation 13 to 1 is assumed the true model, but we estimate 13 to 2, okay, would constitute a specification error. The error consists in omitted variables of x to the power 3. Therefore, the error term in the equations become has a correlations between the estimated this one estimated residual from the equation 13 to 2, and this one is correlation from the previous one here. Yeah, this one. And now the residual become bigger because the residual also determined by x3. Okay. Now suppose that another researchers use the following model. Okay, this one to the power 4. Okay. If equation 13 to 1 is the true model, and equation 13 to 4 also the consistent specification error, the error here including an unnecessary or relevant variable. We call it irrelevant model here. Because here we have bigger residuals. Okay, now assume that there is another model here. Equation 13 to 6. In relation to the true model, 13 to 6 would also constitute a specification bias. The bias here because wrong functional form. Okay. In equation 13 to 1, y appear linearly, here non-linearly. Okay. Finally, another researchers use this one. Y is y hat, y plus residuals, x is x plus wi. E and wi being error measurement. Equation 32.6 as the 7 state is instead of using y and x, we are using the proxies for y asterisk and x asterisk, which might contain the error of measurements. Therefore, equation 13.2.6, okay, has the error of measurement bias. Okay. A specification error sometimes overlooked in the interactions among the regressors. Here we have a multiplicative error term, effect of the one variable. Here is a wage rates, is education, is a gender. Now we have interactive variables. This means education multiplied by gender. Okay, in this model, the change in relative wage with respect to education depend not only on the educations, but also on the gender. Okay, changes in the relative wage with respect to gender depend not only on gender, but also on educations, because we have here multiplicative variables. Okay. Okay. This is the following specification error. First, omissions of relevant variable. That means we drop one variable. That variable is very important for our model, but we drop it from our model. become omitted variables. This is omissions of relevant variable. The second one, we include irrelevant variables. Okay, this also can cause the specification error. Number 3 is using a wrong functional form. For example, our data is linear, but we estimate non-linear model 1. Okay, and the fourth one is error measurements, error of measurements. And number 5, incorrect specification of stochastic error term. Number 6, assumptions that the error term is normally distributed. Okay, before turning to an examination of this specification error, it may be fruitful to distinguish model specification error and model misspecifications error. First, 4 types of error discussed above are essentially in the nature of model specification error. Okay, this is a specification error. This means we have in mind a true model, but somehow we do not estimate the correct model. Okay, in the model's misspecification, we do not know what the true model, but we make the model, we estimate the model. Actually, the model is not the true model. Okay, here, for example, monetarists give primacy to money in explaining changes in GDP, whereas in the Keynesian model, the role of government is more important compared to the money. So if we estimate this, for example, actually we have a Keynesian model, but we use monetarist model. What is the consequences? Okay. Whatever the source of specification error, what are the consequences? To keep these discussions, we will answer this question in the context of 3 variable model. Okay. 1, underfitting a model, omitting relevant variable. Second, overfitting a model. This means including unnecessary variables. Underfitting a model. Okay, we have the very important model, very relevant model, but we drop the variable from our model. Okay, suppose this one the true model 1331, but we estimate 1332. Okay, the consequences of omitting variables as follow. 1, if the left out or omitted variables is correlated with the included variables, okay, the correlation coefficient between 2 variables is non-zero, and alpha 1, alpha 2 are biased as well as inconsistent. Okay, bias. This means it is the worst one compared to the violations of multicollinearity, heteroscedasticity, serial correlations. Okay, this if we omit the important variables, but the variable has correlations with the drop variables, this means we produce bias and inconsistent estimated model. Second, even if x2 and x3 are not correlated, alpha 1 is biased, although alpha 2 is not biased. Okay, or alpha 1 is biased, can become overestimate or underestimate. Number 3, the disturbance variance sigma square is incorrectly estimated. Okay, conventionally measure variance alpha, the variant for this one, is biased estimator of the variant of true beta. In consequences, the usual confidence interval and hypo-testing procedures are likely to give misleading conclusions. For example, okay, suppose we drop very important variable in demand model, income, for example, but we get the price of normal good is negative. This is a misleading results, misleading conclusions, because, for example, for the normal good is negative, but we get positive coefficients. Okay. Another consequence, the forecast based on the incorrect model and the forecast interval will also not readable. Okay. Okay, I explained already. For example, if we, for example, government will impose some policy. For example, if government increase as a policy, decrease price gas or petrol, okay, based on the estimation result. Sounds that the price of gas is insignificant, significant, and inelastic. This is a bias estimated results. So after the government increase price, the demand for the gas, okay, if inelastic, that's mean increase in price, the demand, okay, the demand decrease with the smaller number of compared to the price. Okay. However, because we have a bias estimated results, the demand for gas decrease, okay, significantly. Because the true coefficient of price of the gas is elastic. So this means the government policy become create another variable in our economy. This is the consequences if we use this bias estimated results. Okay. Okay. Second one, inclusions of an irrelevant variables. Okay, or for fitting model. Now we assume that this is our true model, but we estimate this one. Okay, this means we have here x3 is irrelevant variables. Okay, the LS estimator of parameter of the incorrect model are all unbiased and consistent. Okay, expected value alpha 1 is beta 1, alpha 2 is beta 2, but alpha 3 is 0. The error variant is correctly estimated. The usual confidence interval and hypothesis testing procedures remain valid. However, the alphas will be generally inefficient because the variance will be larger than those the true model one. Okay. The point of interest here is the irrelevant variable in model will produce inefficient parameters. If the parameters are not efficient, this means we have a larger standard error. If we have large standard errors, this means we have insignificant parameters. Test of specification error. Knowing the consequence of specification errors is one thing, but finding out whether one has committed such error is quite another. For we do not deliberately set out to commit such errors. Very often, specification bias arises in our model. Yeah. Sorry, I have incoming call here. Okay, how to test for specification error. Okay, one is detecting the presence of unnecessary variable or overfitting model. Okay, suppose we have this model. Okay, however, we are not totally sure that the XK variables is really belongs to this model. Okay, one simple way to find out to test this significance of the estimated beta k with the usual t-test. Okay, we suppose we estimate this equation 13 for 1 and checks which variables are not significant. Okay, but suppose we are not sure that x3 or x4 is a correct model, is correct variable. Okay, and then we use the f-test to detect which variable is a relevant variable in this model. Okay. However, it is not easy to do because we have to, for example, we test beta 2, beta 3, okay, is equal to 0 and beta. Okay, I can write down here. For example, we have 5. Beta 1, okay, beta 2 is equal to beta 3 is equal to beta 4 is equal to 0. Okay, this is one. This is his node. Okay, another his node. Okay, is beta 2 is equal to beta 3 is equal to 0. Okay. Okay. And if we have beta 2 and beta 3 is not equal to 0, and that means we reject. Suppose, okay, suppose we reject the hypothesis of this node of beta 2 equal to beta 3 is equal to 0. This means beta 4 should not be in our model. This means that beta 4 is not. This means the fourth variable is irrelevant variable in our model. Okay, this is how to test this one. Okay, nominal versus true level of significance. Okay, this is process of data mining. Okay, I don't want to explain this one. Okay, test for emitted variable or in conditional form. Yeah. The first one is examinations of residuals. Okay. Examination of residual is a good visual diagnostic to detect autocorrelation or heteroscedasticity. But these residuals can also be examined, especially in cross-sectional data. This one for the cross-sectional case. For the model specification error, such as omissions of an important variable or incorrect functional form. If in fact there are such error, a plot of residual will exhibit distinct patterns. Okay, to illustrate, let us consider a cubic total cost production functions in chapter 7. Okay, this is the model, but we estimate this is a cube model for 1344, but we estimate 1345. Okay, and another researchers estimate 1346. Okay, so what is the correct model? Okay, we use here Durbin statistic. Okay, if we estimate the routinely calculated Durbin version in 13.1, we see that for the linear cost functions, estimated D is 0.716, suggests that there is a positive correlation in estimated residual. And is 10, K is 1, 5% critical D values, okay, 0.879, and for the upper lower limit and upper limit is 1.32. Likewise, the computed D value for the quadratic cost functions is 1.038, whereas 5% critical value is 0.6. Lower limit is 0.697 and upper limit is 1.641, indicating indecisions. But if we use modified D test in chapter 12, we can say that there is a positive correlations in the residual. Okay, because D is less than U for the cubic cost functions. Okay, the observed positive correlation in the residual when we fit the linear quadratic model is not a measure of first serial correlations. But if we use the higher correlation model, we have this problem. Okay, the observed correlation simply reflect the fact that some variables belong in the model, including the error terms, and need to be called out from the introduced in the outright separate variables. If we exclude x3 from the cost functions, then the equation 13.23 has error term in the misexplication model. Okay, because the residual is not only the residual, but is determined also by the excluded variable. Okay, I think you can read this one. Okay, okay. Ramsey test. It is better to use Ramsey test. Ramsey proposed a general test for specification error. We call it reset test, regression specifications error test. Here we will illustrate only simplest version of test. Okay. For example, we have here is a cost output example. Y is total cost, X is output. Now, if we plot the residual for the equation from this 1346 against its predicted value, okay, we saw that's figure 13.2. 13.2. Okay, here we have a certain pattern for here for this graph. Okay. Okay, and here we have a relationship between the residual and predicted value. Okay. Okay. For example here, this would suggest that if we introduce y hat in some form of as a regressor, that means we add this hat y hat to be here, another independent variables, then the R square statistically significant on the basis of this F test. It will suggest that linear cost function, this one, okay, was misspecified. Okay, this is essentially the idea behind the research test. Okay, what is the step to run this research test? First, okay, estimate the model and obtain the predicted value. Run the equations, but you insert the predicted value in the addition as additional variables. Okay, here we have here y hat square and y hat to the power 3. Okay, then R square obtained from equation 437 here is a new R square, and obtained from the 1346 is a old one. So we can use this F test. This F test, okay, F test is a here R square, new R square minus old R square of a number of new regressors. Here we have 2 number of regressors of 1 minus R square, new R square divided by N. N is number of questions minus plus number of parameters in new model. That means here we have 1, 2, 3, 4. We have 4 here. Okay. Now, if F value is significant at 5%, and we reject null hypothesis. Okay. The null hypothesis is correctly specified, and the alternative one is misspecified. Okay, we have here F test. We have a very big number here. F is 284. Okay, Lagrange multiplier. Okay, LM test. How to test this one? Okay, if we compare linear cost functions in equation 1346 with the cubic cost function 1344, the former is restricted versions, and the latter we cause this former, this one, this 1436. The restricted regressions 1346. Okay, assume that coefficient of square and cube output terms are equal to 0. To test this one, we have LM test as follows. Okay, estimated restricted regressions, okay, 1346 by OLS, and obtain the residuals. In the fact that unrestricted regressions 1344 is to the regression, residual equation from 1346 should be related to square and cube output. Okay, this suggests that residual from first step, okay, is significant, has a relationship with the x2 and x3. Here, okay, we run again this residual from the unrestricted one, then run the residual with x and all of the variables. Okay, now take the R square, multiply the R square with N, and compare with the chi-square. Okay, if chi-square from the equation 13412 greater than critical value, we reject null hypothesis. Okay, this one for the example, y is total cost, x is output. Okay, and we get the residual from equation 13413, and we run again this residual with all the variables, and we get r squared here, 0.9x96, and we multiply 10 by this one, we get 9.x96. Okay, we have a degree of freedom is 2 for the chi-square. At 1% is 9.21. That means we reject null hypothesis. Okay, we reject null hypothesis. That means there is a misspecification. Okay, error measurements. Okay, error measurement in a dependent variable. For example, we have equation 13.5.1. Okay, permanent consumption expenditure, current expenditure, and stochastic. Why is not directly measurable? Because no permanent income consumption data. Okay, and then we use unobservable expenditure functions. So y actually is unobservable plus residual. Okay, and then we estimate this one. Equation 13.5.3 here. Here we have residual. Actually, our residual is not the it's residual, but also residual from other equations. Okay. Okay. Then here we have residual as a composite error term containing population disturbance term and measurement error. This means here there is two error term. Okay. For simplicity, assume that expected value of residual is 0. Okay. Error of measurement in y are uncorrelated with x, and covariance of this residual is equal to 0. With the assumptions, it can be seen that beta estimated from the equation 13.5.1 or 13.5.3 will be unbiased estimator. Okay. Error measurement independent variable, we do not destroy the unbiasedness property or LS. However, variant and standard error become bigger from this one. Okay. Okay, this is a explanatory variable. This means we include the permanent income hypothesis one. Okay, I think you can read this one. Okay. Incorrect specification. Let's state. Okay, we have here estimate again here. This is linear regression model, and then we have here omitted variable test. One more test series to add, for example, here. Near singular, okay. Sorry, I forgot this one. For example, we add another variable here, import, for example. Okay, yeah. Okay, LM is not significant. Okay, omitted variables. LM is import. Okay, the test here value to 20 something. F is 1, probability this one. That's when we reject null hypothesis. Okay. And for example here, we redundant variable test. We also include this one. Okay, sorry. We estimate this one, linear regression model, and then simple we include here. Oh, sorry. Okay. Here, redundant variable test, null hypothesis, etching rate. Okay. Redundant variable error is etching rate is not significant. Okay, but it is significant. This means here specification is etching rate is a function of export is function of US GDP and exchange rate, and then we test redundant variable and this is not significant. Okay, the results is significant. Okay, here for example we have restricted test questions. Okay, we have the results here for the as by using T statistic we reject no hypothesis. F statistic also we reject the statistic. Okay, this one restricted and unrestricted model. Okay, and then we estimate again. Yeah, we test for omitted variable. For example, we use here okay, GDP. This is a domestic income. Okay, omitted variable is not significant, but we have here income is also significant in our model. Why? Because most of the imported goods contain some of the exported goods contain imported goods. Okay. Okay, you have any questions?